Like I said, so we're going to do two examples probably just today. I think we're only going to get to two. And the first one's kind of a warm-up. It's similar to the ones that we've seen. Okay, so we'll take a look at that now. But you can think about how, even though they're different kinds of questions, they still follow a same kind of method of how we do it, a pattern. So this one is another open top box, but it's not the one where you cut the corners out. Okay, so it's a little bit different. Open top box has to have a volume of 2,000 centimeters cubed. Find the dimensions that will minimize the amount of material. When you're creating a box out of some material, that material is like the surface area. So in other words, in this case, surface area. I'm actually going to write it out. Surface area is being minimized. What is the formula for surface area? A box is, actually, I'm going to draw it first. A box is like a rectangular prism, right? Now this says square-based, which will be useful, but I'm not even going to worry too much about that right now. Okay, there's my box. And a prism like this has dimensions length, width, and height. Volume is length times width times height. That's not what we're doing here. We're doing surface area. So what do I have? I have this side here, which is length times height, and it's equal to this one over here, so there's two of them. So 2 times length times height. And then I've got this side here, which is width times height. And I've got two of them because this one's going to be equal to that one. And then if this was a full rectangular prism, I would have the bottom and the top, which are length times width. And I would have two of them, except this is open top. So I only actually have one of those. I only have the bottom. And sometimes surface area requires that you think a little bit to build your formula. It's not always as clear-cut as volume, or volume you're usually just using the formula. Straightforward. Sometimes surface area, we've removed a surface or something like that, and you have to think about it a little bit more. All right, now, but that's just generally speaking. For this problem, what do I want to do? How do I want to approach this? What do you think our next step is going to be?
To simplify, since you know it's going to have a square base, you can make W equal to L.
Yeah, so I'm going to change them both to a different variable. I'm going to call them x. So x is the length and width of the box. And just to stay in that same sort of pattern, we'll call the height y, but you could call it h. H would be good too. Let y represent the height. Of the box. So far, so good. So when I start subbing those in, I get 2 times L, which is now x, times h, which is now y. So 2xy plus 2xy. So that's 4xy plus x times x, which is x squared. But again, we need this written in terms of a single variable. And that's where we come over to the side, and it gives us the volume in this case. Volume formula, again, generally speaking, is length times width times height. So it gives us a volume of 2,000 is x times x, so x squared times y, because that's our height. And we're going to solve this for y. And then sub that back in. And simplify. So 4 times 2,000 is 8,000 over x plus x squared. Here's where you might, like some people might want to put this together in a single fraction. We don't usually do that before taking the derivative. We usually do it after, but you could. If you did that, you would end up using quotient rule, but you wouldn't have any simplifying to do after. But so in this case, it's probably easier not to. But again, if this is where without practice, you can get caught up in exactly when you're doing the different steps and sort of make a mistake here. What do you think? We good so far? Happy with this? So what are we going to do now? We're trying to find where this is minimized. We're looking at the derivative of the function. This is the function for surface area. We need the derivative . So go ahead and see if you can find the derivative. It's been a while, I think, but so that's like 8,000x to the negative 1. So you multiply by the exponent of negative 1, which is negative. Then subtract 1 from the exponent, which would be x to the negative 2. So negative 8,000 over x squared plus 2x. And now to remember, to determine where the original function has maximum and minimum points, or possibly has maximum and minimum points, we need to figure out where this does not exist and where it's equal to 0. And in order to do that, in this case, we need to put it together in a single fraction. Okay? So I'm going to multiply this part by x squared over x squared to get a common denominator. And we get 2x cubed minus 8,000 over x squared. Okay, so what's next? And this, again, there's like, not necessarily a right or wrong, like different people might see it a different way. When we were doing this in the last unit, we were doing the simplify fully. That meant one fraction fully factored. There's no rule that you have to fully factor these. That's just not a rule. Eventually, that might be what we do anyway in order to solve. But there's no rule that you have to, at any particular point, have it fully factored. You could common factor out a 2. I'm just going to wait and do it after. We're going to do it anyway, but you could do that. If you could factor this and somehow simplify it, then that would be worthwhile. Where does this not exist? At 0. When x is 0. So tell me something about that. What's going on when x is 0? Huh? The top would not be 0. This part would be 0, but it'd be negative 8,000. But it won't work. So, I mean, it's not. I think it probably is, yeah. In the derivative. What else? No, it's not. I don't think it's going to be a cusp. I think it's going to be an asymptote. Because we had it in the original function as well. We had a denominator of x. Like if we had come up with a common denominator here, it would be a vertical asymptote. But tell me something about this problem. Why? The function wouldn't exist. The derivative doesn't exist. But there's another way that we can think about this. Yeah, like what kind of, like, is that really minimizing surface area when one of my dimensions is equal to 0? Like that doesn't make any sense. So there's ways that you can think about this in terms of the math. But I like, in this case, the real life way of thinking about this. Okay, x can't be 0. That's a nonsense answer for this problem. When we're doing sketching, it might mean something else. I can think about it in terms of this problem. This is inadmissible. So I don't even have to decide if it's a cusp or if it's an asymptote or exactly what it is. We don't have to worry about that because we know in the context of this problem, it just doesn't make any sense. So that means we're going to figure out where this is equal to 0, where the derivative, sorry, not the original function, where the derivative is equal to 0 is where the top, since I have it as a single fraction, is where the top equals 0. So this is 2x cubed minus 8,000. So now I can divide both sides by 2 and just get rid of it instead of factoring it and holding on to it. I just waited to do it here because I knew it was going to be gone when it's equal to 0. And tell me if you remember this. If you were in my class at least last semester in MHF, I like to talk about when you have, now that's not a great difference of cubes. It looks like it might be, but 4,000 is not a perfect cube, so that would be hard to factor. But let's just say it was a difference of cubes, x cubed minus 27, right? And let's say we were solving this equal to 0. So this is something that I like to talk about because I think it's helpful and interesting. So I would factor this, right? So I'd get x minus 3, x squared plus 3x plus 9, right? So what are my solutions? When this equals 0 or when that equals 0? But when will this equal 0? This one's when, yes, the whole thing is 0 when x is 3. That's right. So that's one of our solutions. But what about that? Will that ever have a solution? It'll never have a solution. It can't. I think of this like this. If I graph this, this is like a cubic function, y equals x cubed, with a vertical shift down 27. Right? That's all it is. And what does just a standard cubic function look like? It looks like this. So one solution when x is 3. It can't have more than one. Other cubic functions can, because another cubic function could go like that. But this kind, when it's a sum of cubes or a difference of cubes, will never have more than one solution. It'll only ever have one. That's exactly right. But I would wonder if some people would be like, well, but so that's what we're going to do here. That was the whole point of talking about this, is it's easier to just do this, isn't it? Don't factor it, even if it's not really factorable because 4,000 is not a perfect cube. But even if it was, don't get caught up and try to factor when you can just solve it like this. So then x equals the cube root of 4,000. But like, the point is, some people might wonder, but if I do this, aren't I losing those other solutions that would have come from that other part? But you're not. So it's fine to do that, and it's actually efficient, and it's the right way of doing it. This works out to about 15.87. We already talked about where the derivative does not exist. We've already managed that. There's only one place where it's equal to 0. So now our last thing we're going to do is we're going to check this value, which, like I said before, is good for two reasons. We'll talk about that. And then usually we have to go and find the other dimension or something like that and make a final statement. So why do we do the check? Well, for one, it's just checking your work. Like if you made a mistake, you'll probably notice in the check. That's not a guarantee, but I would think it's likely that if you made a mistake in your math somewhere, your answer is going to be wrong enough that your check will catch it. That depends a little bit on how close your values are that you're checking, because we're going to check 3 values. Notice that in this case, I'm checking quite close to my value. You could go even closer, 15.5 and 16. Like you could go as close as you want. There's no reason why I picked the ones that I picked, except that I've got the answers to these 3 written in front of me, so I don't have to punch it into my calculator. It speeds things up. That's why I'm picking them now, but why I picked them in the first place, I have no idea. So this one worked out to approximately 758.3. This one was approximately 755.95. And this one was, I think, exactly 756, worked out exact. So 2 things. This shows that the value that we calculated is less than, we're trying to minimize, so it is less than, it is less than a couple other values that are close to it. It would be strange if you got an answer where that worked out, but you got, but your answer was wrong. I think that would be strange. So you're probably pretty sure that you might have rounded wrong or something like that, but you're in the ballpark. You're pretty close. Okay. Again, depending on exactly the numbers you choose to check. If I picked 0 and 50, well, that's a terrible check. That's not really checking anything, right? But also, you can have a derivative. This isn't something we've talked about a lot, but we've talked about it a bit, and we'll see it more when we start to sketch. It doesn't come up very often in these questions. You can have a place where the derivative equals 0, but it's not a maximum or minimum point. It's not a local max or min. You can have a horizontal tangent line where the derivative would be 0, but it's not a turning point. That can happen. Okay? So part of this check is we're also just checking to make sure that it's not some other kind of horizontal tangent line. That it, in fact, does turn, and it is a minimum or maximum, depending on the question. Now, we set these questions up in such a way that they always work out. But in general, it's possible that you could do everything right, come up with an answer, and it's not a local max or min. So that's another reason why we do the check. Okay, so when x is 15.87, I'm going to find y, which was 2,000 over that number squared, which is about 7.94. So it's 15.87 centimeters by 15.87 centimeters by 7.94 centimeters. Questions about that? Happy with this? All right, next one. Again, you've got this in a handout, right? So you don't have to write this down. You can write it down later if you want. This one's new. This one's very different. It would be hard, I think, to do it all by yourself, start to finish. There's a couple little tricks, but it ends up being one of the types of questions that we do. So once you've seen it once and practiced it a couple of times, you should be able to do it. But there are definitely some easy places to make a mistake. And So, you got to make sure that you've practiced it and that you really get it and that you can do all the little details. Otherwise, it won't come together, or you won't be able to figure out why if you're doing it for the first time on a quiz or a test. Keep that in mind. I think the handout has 2 questions like this, but we only have time for one. It's going to take us a bit of time to do this. You can do the other one if you want on your own. The other thing that, if you did the homework, hopefully you did. You had a whole week to do it, so I hope you did. But the last question in the homework had an extra level to it. Do you remember that question? It had something to do with cost. So it was different. We didn't do an example like that together in class, and we're not going to. This one has to do with cost as well. It's sort of similar, but you want to have tried that. If you didn't do the homework at all, at least go back and try question 6. I think it was 6. It was the last one from that handout. Okay, it had an extra layer, an extra element to it. And after we've done this one, it might make it a little bit easier. Okay, so a powerhouse is located on one bank of a straight river that is 200 meters wide. A factory is 400 meters downstream and on the other side of the river. Laying cable underwater costs $12 per meter, and laying cable underground costs $6 per meter. What path should be chosen to minimize cost laying the cable? Again, this is where those steps or those tips can be very useful, in particular if you have a question that's got a twist to it or anything different, or it's a new type of question. Because you would read this probably and be like, I don't have a clue what the solution to this one is going to look like. But that doesn't mean we can't get the question started. So what could we start with? A diagram. Very nice. The other thing we could start with is because we always like to state what is being maximized or minimized. So we could notice that we're minimizing cost. Cost, C, is to be minimized. So I'm getting ahead of myself here, but that means I'm going to come up with some formula, C equals. Right? And if you're doing a surface area question that involves cost, you're not doing an equation for surface area. It'll be related to surface area, but you're making an equation for cost. So that's where it helps to really think about this. But let's get back to our diagram. So first I'm going to draw the river. Try to keep those lines parallel as much as you can, because they're supposed to be. Whoops, what happened there? Okay. And then what do we do? This isn't very good so far. Well, I've got my powerhouse at point P, and I've got my factory at point F on opposite sides of the river. And now what does it tell me? What does it, what else can I do? What can I continue with? So the distance, thank you, from here to here is 400 meters. Is that right? Good. What else can I add to this? The river is 200 meters wide. Good? Now what? So let me help a little bit here. Don't write this down. We're just going to think a little bit about this before we continue, because it really, I think, helps to have a good understanding of what's going on here. So we're going to explore this a little bit before we can continue solving it. What if I just said, I just want to run the cable all underwater? That would be that, right? Forget about going on land. Why wouldn't you want to do this? Yeah, it's more expensive underwater. Okay? If it was the same cost for underwater and for on land, then that's probably what you would do. The calculation method that we're going to use would find that anyway, but That's what you would do, right? You would minimize if it costs the same, you'd just minimize the distance, and that would be the distance. But it costs more to go underwater. How much would it cost if I chose to do this? How would we figure that out? Remember? Okay. Yeah. So this length would be the hypotenuse of a right angle triangle that goes like this, right? With side lengths 200 and 400. Is that right? So it would be, so I'm just going to do this quickly on my calculator. I'm finding the hypotenuse, so it's going to be the square root of 200 squared plus 400 squared. 447.21. What do I do with that? Multiply by the cost, which underwater is $12. So I take that and I multiply by 12, and I get about 5366.56. If I went all the way underwater, that's what I would get. What would be another option? What if I'm like, I think it's really expensive to go underwater, so I'm going to minimize the distance underwater. How would I do that? I would go straight across, and then I would go along land the entire distance. What would be the cost of this one? $400 times 6 is the cost and distance on land. 200 times 12 is the distance underwater times the cost, and that gives me 4,800. That's actually exactly 4,800, not approximately. So that might be the minimum. If going underwater was way more expensive, then that might actually be the minimum. Okay? But what do you think is happening here? There might be, maybe this is the minimum, I don't know, but definitely that's not the best choice. That's the least distance, but it's more expensive at least in this extreme. Remember when we did that process of max and min on an interval? Well, I've just found my interval. These are the two options that we can have, right? These are the two extremes. Because I wouldn't go diagonally this way. I wouldn't go further that way. There's no way that's going to be cheaper. So these are my extreme bounds. You don't have to calculate this every time. We just did it this time because we're gonna find the answer, but it's, I think, useful to think about what's happening here. Now I have a little demonstration as well that can help speed things up. So take a look. There's one extreme all the way across. Notice that this is 400 and this is 200. So if I went all the way across, look, same answer we got. The cost on land was 0 because we didn't go on land at all. So the cost for water was 5366.56. Notice that that's the cost that we found there. And so the total is obviously the same thing. And what if I went all the way to the other? There's your 4,800. Land was 2,400. Water was also 2,400. And the total was 4,800. But watch what happens when I go like this. It was started at 48. It goes down before it goes up. So there is some minimum between those two extremes. And I could kind of narrow it down like, so I'm at about 100. Actually, let's go, I'm at 80. And what is that 80? I don't know, but I'm at 80 and I'm at 45. It drops below 4,500 and then goes back up to 4,500. So my, whatever X represents, we haven't even talked about that yet, but whatever X is will be somewhere between 80 and 150, I guess. So help me out here. Actually, let's do one more thing. So what we know is the minimum cost will be when we travel to some point through the water and then cover the rest of the distance on land. Okay? That was just a demonstration that happens to be true in this case. You could, like I said, if the cost underwater was so much more, like $1 million a meter or something, then it might be that the minimum would just be straight across. But most of these, it's going to be somewhere in the middle, because that's how we like to set them up. So what do we do now? We're not quite there yet. We got to add some labels to our diagram here before we can actually start writing an equation.
Can we create a triangle and work with the angles since we know the water is quite small to twice blended this out?
So like trigonometry, are you thinking? You might be able to solve this question that way, but we don't know how to do derivatives of trig functions yet. So that wouldn't work for us right now. So there's a way we can do it without trigonometry. We don't have to worry about the angle. We need some variables in here.
Like when you take the derivative for like a cosine or something, you just flip it, like change cosine to sine.
Let's talk about that next unit when we talk about trigonometry. We don't have time to get into that right now.
That's how it works. It's like,
There is a relationship there, but it's going to be a little bit more complicated than that, because there's, like, what do you do when you have other things involved and that kind of stuff. So let's worry about that. That's a big topic that we'll cover next unit. What are my unknowns? What do I need to find out? Don't I need to find out that distance? What distance from where we started, but on the, whoops, that should be more sort of across from here. Don't we need to know what that distance is? Very nice. So if I call this x, then on the other side would be 400 minus x. And it turns out this is a better way to do it than, some people might let x represent the distance on land. Turns out that would make this question trickier, I think. So it's better to let this be x. What's our other unknown? That is going to have some factor into all of this. Well, don't you think it's the length that we go underwater? So we'll call that y. And as we saw in that demo, this is my x now. And as I increase x, I'm also increasing y. But I'm decreasing the length on land and increasing the length underwater if I go this way and vice versa the other way. So we have to find that sweet spot. So how are we going to do this? Well, anybody have any suggestions? Yeah. Yep. So how are we going to do that? So remember, we want to minimize cost. We want to find the x that minimizes cost. We're not minimizing distance. We're not minimizing 400 minus x. We're not minimizing y. We're minimizing cost. So we have to come up with an equation for cost. This is where doing this thing here, cost is to be minimized. So cost equals, that's why this is useful. So how am I going to come up with an equation for cost? How much, given what we've done here, what will be the cost for our land, for burying the cable on land? Right. So let's do that. 6 times 400 minus x. What will be the cost underwater? $12 times the distance, which is y. So isn't that going to be plus 12y? So we had to factor in the costs. And now we've got an equation for cost. But what's wrong with our equation? 2 variables. We need 1. So how am I going to write y in terms of x? Sure can, and we sure will. Y squared equals x squared plus 200 squared. Y equals the square root of x squared plus 200 squared. Can we simplify that any further? I don't think so. So now we take the derivative. So if you had your x in the wrong place or your y in the wrong place or like any of this stuff out of order, and if you don't understand the relationships of how we got here, this is a really tricky question. You've never seen anything quite like this before in any other grade, I don't think. So like this one is trickier, right? So I'm going to do this quickly. If you wanted to take 2 steps, that's fine. But this is a square root is to the 1/2. Exponent 1/2. So 1/2 times 12 is 6. Times the derivative of what's inside. And then when I subtract 1 from the exponent, it becomes negative 1/2. So it's over the square root of x squared plus 200 squared. Again, we end up doing square root functions enough that you could probably do that without rewriting as a exponent, like with an exponent, and then doing every step, and then, you know, do it in 1 step if you can, but if you can't, take a couple steps, that's fine too. But you got to understand how we got there. So this is 12x over the square root of x squared plus 200 squared minus 6. Now, what was the whole point of this? We take the derivative where the derivative does not exist and where it's equal to 0 are where you might find maximums and minimum values, local max and local min. So I have to figure out where this is equal to 0 and where it does not exist. So somebody tell me something about this. Okay, fair. What do we usually do at this stage? How would we do that? Emery, what do you think? Yeah, usually we simplify, maybe not simplify fully, but we simplify more and put it together in 1 fraction. But there's no rule that you have to. In this case, I don't think we do. Now, maybe it's easier for you to just do that, that's fine. But this is where like a preference comes in, and your personal skill level or the way you approach problems will vary a little bit from person to person. But in this case, I don't think we have to. If I was going to put it together in a single fraction, what would I do? I'd get this as my common denominator. So I can just look ahead and I can say, well, that's going to be the denominator, right? So where will this not exist? When the denominator is 0, or if you're taking the square root of a negative, when will that happen? Nowhere. Thank you. Right? Whatever I put in, whether I put a positive or negative x in, you never would put a negative x. What would negative x be in this case? It would be going this direction. Like you wouldn't do that anyway. So we could discount those just because they're kind of ridiculous, right? But let's just say you put a negative x in, you're squaring it and adding a positive anyway. And this will never be 0 because I can't get this equal to the negative of that, which is 40,000. This will never be negative 40,000. You're squaring it. It's always going to be positive. This will never be negative. This will never be 0. C prime at x exists for all x. So that's out of the way. So now we got to do C prime at x equal to 0. Now, if we put it together in 1 fraction, the math is going to be kind of similar anyway. So I don't know that there's like a lot of value to doing it this way versus the other way. It's just a preference thing. But I'm just reminding you that like, don't get too caught up in strict rules. You want to be more versatile than that. So this is where 12x over square root x squared plus 200 squared minus 6 equals 0. So what am I going to do? Move the 6 to the other side. Multiply by the denominator. Divide both sides by 6. What next? Yeah, nice. Square both sides. 4x squared equals x squared plus 200 squared. And I end up with 3x squared equals 40,000. Remember, the negative 1 doesn't make any sense. And that works out to approximately 115.47. Remember when we were doing the sliding back and forth and we noticed that it was like between 80 and 150, and if you were watching carefully, you could have narrowed it down to even somewhere between kind of 110 and 120. So there you go. That already fits for what we looked at, but we're going to do a check just to be sure. Any questions so far? There is one last step to this question that's tricky. So let's do the check first. I don't know why I chose these values. I think if I were doing this again, I'm going to use the same values because, like I said, just to save some time, I've already got them written down. But these are a little wide. I say, why not pick values that are very close, like 115 and 116. I think those would be better to use. I don't know why I chose these ones, but that's what I did. Someday I'll fix it. All right, so this one worked out to about 44.7905. This one worked out to 44.7846, and this one worked out to 44.78.86. So there you have it. Looks good to me. So I'm going to go ahead and find the other values that are involved. So x is 115.47. 400 minus x works out to 284.53, and y is about 230.94. And the last tricky part of these questions is just writing the therefore statement, because what are you going to say? If the question just says how much cable should be laid underground or along the land to minimize cost, then it's easy. You just state that, or how much should be underwater, then it's easy. But what path should be chosen? So I'm going to say, therefore, 230.94 meters of cable go underwater, water, to a point that is 284.53 meters from the factory. And then the rest is underground. Something like that. Any questions? Yeah.
This question would be enough to say
I'm not too worried about you getting the exact wording or whatever that I'm looking for, as long as what you say makes sense. I'm not going to be too worried about it. All right.